So, in the fourth module of this series of the lectures on the welding engineering, this fourth module is based on the arc welding processes, and under this this is the seventh lecture which will be based on the gas metal arc welding processes. In this one will be talking about first the basic principle of the gas metal arc welding processes, then we will see that what are the important parameters related with this process and how do they affect the quality of the weld, and we will also see that how the metal is transferred during the welding by this process, and what are the important areas of applications related with this process. So, starting with the content of the process, fundamentals of the gas metal arc welding process, which is also known as GMAW, or the gas metal inert gas, that is MIG, or gas metal arc welding process, that is GMAW process. What are the power sources that are used with the process? Normally we go with either constant current power sources or the constant voltage type of power sources. So, depending upon the electrode diameter, the suitable type of the power sources is selected. Then the different gases that are commonly used with the metal inert gas welding processes, that is like the argon or helium, or the mixture of argon and helium, and the mixture of other gases. Then what are the important the parameters related to the gas metal arc welding process, and how do they affect the quality of the weld joint. We will also try to look into that how the metal is transferred in the gas metal arc welding, and what are the conditions that affect the modes of the metal transfer. And one variant of the gas metal inert gas welding process is the pulse gas metal inert gas welding. About that we will also try to see that the basic principle of the pulse GMAW or the pulse MIG welding process. So, starting with the principle, this of the gas metal inert gas welding process, this process basically uses the heat generated between the consumable electrode and the base metal for melting the fairing surfaces of the base metal, so that the metallic continuity can be obtained for developing the weld joint, and for protecting the weld pool from the atmospheric contamination. In this process, the inert gas or the inactive gases are used. So, this is the basic principle where for developing the weld, melting of the fairing surfaces is obtained using the heat produced by welding arc, which is established between the base metal and a consumable electrode. So, differing from the GTAW process, where the non-consumable electrode is used, in this process the consumable electrode is used just like in submerged arc welding process, but in this process, for protection of the weld pool, inert gas or inactive gases are used. The welding arc and the weld pool in this process are well protected by a jet of the shielding inert gas or the inactive gas, which is coming out from the nozzle and forms the complete shroud around the arc zone and the molten weld metal, so that the atmospheric gases can be kept away from the weld zone, and the molten metal can be protected from any adverse effect on the quality of the weld metal. So, the basic thing here is that the melting of the fairing surfaces of the base material is ensured using the heat of the arc, which is developed between the base metal and the consumable electrode, and to protect the weld pool from the atmospheric contamination, the shielding gases are used. These shielding gases may be inert gas or the inactive gases for the shield. So, this the diagram, schematic diagram showing that this process in this process the arc is established between the electrode, which is fed continuously from the spool of the electrode through with the help of these feed rollers, and the power is supplied through the suitable type of power source. It can be of the constant current or the constant voltage type, Then the terminals of the power source are connected to the electrode and the base material to complete the welding circuit, and inert gas or the inactive gas mixture is supplied from the gas cylinders to the welding torch, and then when it comes out of the nozzle forms a complete jet around the arc and the weld pool, so that the weld metal can be protected from the atmospheric contamination, and any adverse effect on the weld metal can be avoided. The gas metal is found significantly different from the tungsten inert gas welding process, in the sense that it uses the consumable electrode, while in case of the gas tungsten arc welding process, non consumable electrode is used. And the second thing, the arc gap in case of the gas metal arc welding process is found to be greater than that of the GTAW process, and because of these differences, the significant difference in the quality of the weld which is developed by GMAW process is obtained than that is developed by the GTAW process. So, MIG welds are not considered as clean as the are produced by the GTAW or the TIG welding process. The difference in the cleanliness of the weld is attributed to the various factors, and that is mainly due to the variation in effectiveness of the shielding gases which are used in the two processes. The effectiveness of shielding gases to protect the weld pool is found to be different in case of the gas metal arc welding process than the gas tungsten arc welding process, and this difference is caused by the two factors. One is the stability of the arc, and the second is the arc length or the gap between the electrode and the workpiece. So, that is what we will see further. So, the cleanliness of the weld by the two processes is significantly governed by the effectiveness of the shielding process, which is found different in the two processes. So, if we see effectiveness of the shielding in the two processes mainly determined by the stability of the arc and the arc length, as I have just said. So, if the arc is stable, then we will be getting the better shielding effect, and if the arc is short, then also we will be getting the better shielding effect, because the gases will not be able to reach to the arc zone and to the weld metal to have any adverse effect. So, in case of the GTAW process, arc stability is found to be much better than the GMAW, because of the presence of the non consumable tungsten arc, which can emit the electrons very easily, and that is why the stability of the arc in GTAW process is very good, which ensures that arc is always covered with the shielding gases effectively, and helps to that in turn helps to protect the weld pool from the atmospheric contamination. Further, in the GTAW process, the arc length is found to be the much lower than the GMAW, and that is why the possibility for the presence of the atmospheric gases in the arc zone is further reduced, and which in turn helps in producing the better and the cleaner weld by the GTAW process than the GMAW. In case of the GMAW arc is relatively longer and it is less stable than the GTAW process. So, the difference in the stability of the arc in case of the two processes is mainly attributed to the presence of the consumable electrode in case of the GMAW process, and in case of the GTAW process, non consumable electrode. And the electrode material is the another factor, because in case of the GTAW process, we use tungsten electrode, which helps in developing the very good and stable arc, while stability of arc is not that good, because in GMAW we use the filler material either of aluminum, steel as per the requirement, and these materials are not that good electron emitting materials, and that is why the stability, because of the type of the electrode material, is found to be poor with the GMAW than the GTAW process. So, the consumption of the electrode during the welding further decreases the stability of arc. We know that in Gmaw electrode is consumed continuously by melting of the electrode tip, and because of this consumption welding stability of arc is slightly decreases as compared to that of the non-consumable electrode which is used in case of the GTW process, and therefore, shielding of the weld pool is not as effective in case of the GMAW process or MIG process as in case of the TIC process. Thus, the GMAW is similar to the GTAW except that it uses automatically fed consumable electrode, but the cleanliness is not that good. Therefore, GMAW offers the because of the use of the consumable electrode which is fed continuously in case of the GMAW or MIG welding process, it offers the much higher deposition rate, and that which in turn helps in achieving the higher welding velocities, and also the quality of the weld is reasonably good, and that is why the GMAW process is extensively used in industrial fabrications where good quality weld joints are required. And therefore, consumable electrode in this GMAW process fed automatically, while the torch is can be controlled manually or automatically. So, based on the kind of control which is available by a given the GMAW process, the process can be used for comparatively thicker plates of the reactive metals which can be adversely affected by the environment at the high temperature. So, since this process uses the continuously fed consumable electrode, and that in turn helps in achieving the higher deposition rate and the higher welding speed, and the proper shielding of the weld pool by the inert gas or the inactive gases in the GMAW process helps in successful welding of the reactive metals like aluminum, magnesium and the stainless steel. Because of the chromium presence, these can help in these, and because of this cleaner weld, these are extensively used in industrial fabrications. Now, we will see that what are the power sources which can be used effectively in the GMAW process for developing the sound weld joint. The GMAW process can use either constant voltage or the constant current type of the power source depending upon the electrode diameter. So, these are the factors mainly which affect the kind of power source which can be recommended. Normally, for the large diameter electrodes the constant current type of power source is recommended, while with the small diameter materials the constant voltage type of power sources are recommended, so that the self regulating arc can be achieved. Materials like the electrical resistivity of the material of the electrode also affects the selection of the power source, but for a given diameter. If the material is of the higher electrical resistivity, then it will result in the greater resistance, and so it will respond in better way with a constant voltage type of power source for achieving the self regulating arc as compared to the constant current type of power source. So, the materials like copper and the aluminum of the higher electrical conductivity with a large diameter, it is preferred to use the constant current type of power source rather than the constant voltage type, because in those cases the melting rate will not be much affected by the electrical resistive heating occurring due to the flow of the heavy current. Further, the electrode extension also affects the type of power source which can be used in. Further looking into the effect of the electrode size on the selection of the power source in case of the small diameter electrodes lesser than the 2.4 mm, electrical resistive heating controls the melting rate of the electrode predominantly, and under these conditions constant voltage type of power source with the DCEP, that is the direct current electrode positive polarity, is used to take the advantage of the self regulating arc, so that the arc length can be maintained using the constant voltage type of the power source. While in case of the large diameter electrodes, the constant current type of the power source is used with the variable electrode feed drive system to maintain the arc length, because in these conditions the variation in the current does not affect the melting rate of the large diameter electrodes, and this one is also applicable for the metals or the electrodes of the high electrical of the low electrical resistivity or good electrical conductivity. If you see this diagram simply shows that what happens when the constant voltage type of power source is used with the varying arc lengths. We can see that when the arc length is increased, then operating point shifts from 1 to 2 and then 2 to 3, and because of these shifts in the operating point due to the increasing arc length, there will be reduction in the welding current, and this reduction in welding current will be affecting to the melting rate. So, this helps in obtaining the self regulating arc. Then we will see the polarity and its effect in the gas metal arc welding process. It is generally the DCEP, that is the DC electrode positive polarity, is normally used in case of Gmaw welding process, and DCEN is rarely used because the DCEP offers the advantage of the stable arc, smooth metal transfer, low spatter, and the good weld width characteristics over a wide range of the welding current. So, because of these advantages, DCEP or straight reverse polarity is normally preferred over the DCEN, which is the straight polarity. So, DCEN because results in many unfavorable characteristics like the unstable and erratic arc, and the short circuiting and the buried arc is also developed under these conditions. Further, it results in the lower penetration rate. However, the higher melting rate can be achieved when the DCEN is used. So, except the benefit of the having higher melting rate, other and the features related with the DCEN are unfavorable, especially the lower penetration, unstable and erratic arc. Use of the AC in GMAW is not very common due to the two factors. One, arc shows excessive extinguishing tendency, means arc tends to go off, So, and the arc is found the erratic. So, because of the two reasons, the AC is found very poor acceptability in case of the GMAW process, and that is why it is not preferred. Apart from the power sources and the effect of the polarity or the polarity selection, the gas which is used for protecting the weld pool from the atmospheric contamination also affects the other many other characteristics of the weld joint or the characteristics related with the welding, and the shielding gas affects the arc characteristic and the metal transfer characteristic. We know that the helium and the argon and the modification of the argon by the other gases affects their ionization potential. So, if the shielding gas is having the higher ionization potential, then it will result in the different arc characteristic than one having the lower ionization potential. So, if the arc characteristic is so if the ionization potential is more, then the arc characteristic will be on the higher side with respect to the voltage, and shielding gas also affects the metal transfer characteristic. For example, argon leads to have the different type of the metal transfers like the globular transfer and the spray transfer, but when we shift to the CO2, it hardly affects the mode of metal transfer, rather it causes the great large amount of the spattering during the welding. We will see these things further in the coming slides, how the characteristic and the metal transfer is affected by the shielding gas. Depending upon the effect of the shielding gas on the heat generation, penetration is affected. For example, the helium causes the higher ionization potential. Because of the higher ionization potential develops a lot of heat, and which in turn helps to increase the depth of the penetration, and the width of the fusion is also affected. The welding speed, the more heat generation by the helium causes the effective transfer of the heat to the base metal. So, the rapid melting helps to increase the welding speed, but the higher flow rate of the helium is required as compared to the argon. So, depending upon the way by which shielding gas is affecting to the heat generation, so the melting of the base material, which in turn will be affecting to the welding speed. Further, the quality of the weld is also affected by the shielding gas which is being used, like the argon and helium offers very good quality welds, but when these are modified by the oxygen or the CO2 is used, it adversely affects the quality of weld due to the presence of the oxygen in the arc region. Further, if there are other gases as additives in the shielding gases, then these can affect the metal element transfer efficiency. That is about that what percentage of the elements being transferred from is transferred from the electrode tip to the weld pool actually, because some of the elements are lost due to the oxidation or the other gas effect of the adverse effect of the other gases present in the arc zone. So, if the gas if the gases are not pure and having a lot of impurities, then these impurities can react with the elements being transferred during the welding from the electrode tip to the weld pool, and because of this the reduced percentage of the elements can be there in the weld metal, which in turn will be decreasing the elemental transfer efficiency. So, and a decreased elemental transfer efficiency will be leading to the difference in the weld metal composition. Now, we will see in detail about the shielding gases and their role in the GMAW. Like the GTAW or the TIG welding, the shielding gases such as the argon, helium or CO2 or their mixtures are used for protecting the weld pool from the atmospheric contamination. The effect of these gases on the MIG welding is similar to that of the TIG welding, because primarily their role is to protect the weld pool from the atmospheric contamination, at the same time also affect the kind of heat which is being generated during the welding, so that desired depth of penetration can be achieved. Moreover, the shielding gases also affect the mode of metal transfer in case of the GMAW process from the consumable electrode to the weld pool, which is not observed in case of the GTAW, because GTAW uses the non-consumable type of the electrode. If we see in case of the arc welding process, if when we use argon, very deeper penetration and the narrow weld bead is obtained with the metal transfer ranging from the globular to the spray. The mixture of the argon and helium results in the optimum penetration, and in terms of the penetration and the weld bead. Helium further causes the optimum the weld bead cross section, while the CO2 results in a lot of spatter and the large size of the weld pool. If we see in case of the CO2, metal transfer is not much affected by the increase in current, while in case of the argon, increase in current significantly affects the metal transfer mode from the globular to the spray. So, MIG welding with the argon as a shielding gas results in the significant change in mode of metal transfer from globular to the spray and rotary transfer with the minimum spatter, while the helium produces the globular mode of the metal transfer. The MIG welding with the CO2 results in the weld joints with the spattering. So, spattering is commonly encountered when the CO2 is used as a shielding gas. So, a shielding gas also affects the width of the weld bead and the depth of penetration due to the difference in the heat generation during the welding. So, the way by which heat generation is affected due to the variation in the shielding gas being used, the weld bead cross section can be influenced with the change of shielding gas, and that change can be observed in respect of the weld width of the weld bead and the depth of the penetration being taking place. So, and now we will see what are the important welding parameters that play a significant role in development of the sound weld joint, the deposition rate, and the width of the bead, reinforcement of the bead, and the quality of the weld joint. So, now we will see the important parameters that affect the various important aspects related to the Gmaw are the welding speed, welding current, the electrode angle, electrode extension, the welding voltage, welding speed, and the welding position. One by one we will be trying to look into the details of each of these current. In general, the increase in welding current increases the depth of penetration and the melting rate of the electrode. So, the deposition rate, higher deposition rate is achieved. The electrode angle, it can be perpendicular to the plate, or the it can be at certain angle from the normal position. So, when the electrode is pointed towards the welding direction, we call it as a forward welding, or when we point the electrode tip towards the opposite to the welding direction, then it is termed as the backhand welding. And forward welding results in the shallow penetration and the wider bead, while the backhand welding results in the deeper penetration and the narrower bead. So, that is how it affects the weld bead cross section. Also, the electrode extension affects the width of the weld bead and penetration. At the same time, deposition rate is also affected because of the electrical resistance heating. The welding voltage has the marginal effect on the weld characteristics of the weld joint, but marginal increase in range of marginal increase in voltage increases the width of the weld bead. And in case of the welding speed directly affects the depth of penetration and the weld bead reinforcement and the weld bead width. So, the with the increase of the weld bead, the reinforcement increases depending upon the kind of the electrode diameter which is being used, but for a particular optimum speed, maximum penetration is achieved. Higher and lower welding speed results in the lower penetration and the different shapes of the weld bead cross section. Then welding position affects also affects the quality of the weld which is being made, and how that can be made. For example, in the normal downhand position or the flat position welding, spray transfer can be effectively used for developing the weld joint at a high deposition rate, but in case of the odd position or vertical positions, the pulse welding is found to be more, pulse MIG welding is found to be more useful. So, now we will see these effect of these parameters on the quality of the weld joint one by one. So, the welding current mainly affects to the weld penetration, because and these all these effects are mainly observed because of because of the variation in the heat being generated during the welding due to the variation in the welding current. In general, the increase in welding current increases the heat being generated during the welding. So, greater the heat generation, greater will be the penetration and during the Gmaw process, which in turn will also be increasing the deposition rate due to the increased melting rate of the electrode. Further, it also affects the weld bead geometry, because a higher welding current can lead to the deeper penetration, and the weld bead cross section can also increase because of the increase in cross section, increase in the welding current. The quality of the weld is also affected in terms of the mechanical performance, or in terms of the defects. Say very low welding current will be leading to the very low heat input, which can increase the porosity, but too high use of the too high current can lead to the development of the defects like undercut, or significant coarsening of the and the structure in the heat affected zone and in the weld region itself. So, the selection of the optimum current is important from the weld penetration, deposition rate, the weld bead geometry, and the weld quality point of view. Now, like another important the parameter is the welding voltage. We know that the welding voltage has the marginal effect on the quality of the weld and weld bead, but if we increase the welding voltage over a narrow range, then the increase in arc voltage affects the width of the weld bead. In general, an increase in arc voltage increases the width of the weld bead. If you see this diagram shows the direct relationship between the rate at which the electrode melts, means the electrode deposition rate, and means the metal deposition rate, or the welding current. If we take the large diameter electrode, and here say for the small diameter electrode of 1 mm, say that how the increase in welding current will be affecting to the electrode burn off rate, or so the metal deposition rate by the Gmaw process. In this case, if we see that when the current is increased slowly, increased at a low level, then the relationship between the burn off rate and the welding current is almost linear, but when we go on the higher side, then the relationship between the electrode burn off rate and the welding current tends to be the non-linear, and this non-linearity at the upper end of the welding current range is encountered mainly in case of the small diameter electrodes than the large diameter electrodes, and it happens only in the higher end of the welding current range, and this happens because of the increased effect of the electrical resistance heating when the high current is used with a small diameter electrode. While when the current is small, even with the current is low, even with a small diameter even with a small diameter electrodes, the linear relations largely linear relationship exists between the welding current and the burn off rate. If we see that even when we are using too high welding current with a large diameter electrode, this relationship still remains of the linear kind. So, this is what we can see, the electrode diameter and the welding current significantly affects the deposition rate. For a given diameter of the electrode, increase in welding current increases the deposition rate significantly. So, welding current is primarily used to regulate the overall size of the weld bead and the penetration. So, higher is the current, more will be the heat generation, higher will be the melting rate of the electrode, which in turn will be increasing the weld bead cross section, and the depth of penetration will also be increased. While the too low welding current results in piling of the weld metal on the fin surfaces, as the weld bead instead of the penetrating into the workpiece, which in turn increases the reinforcement of the weld bead without the enough penetration. So, there are two adverse effects are related with the too low welding current. One is unnecessary reinforcement of the weld bead without significantly penetrating into the workpiece. So, the poor penetration can lead to the premature failure of the weld joint. While the excessively high current due to the excessive high heating of the workpiece due to the too high current can lead to the weld sagging, and that is why optimum current gives the optimum penetration and the weld bead width. Electrode extension is another important parameter that affects the deposition rate and the weld bead cross section. Electrode extension is basically the length of the electrode which is coming out of the contact tube and the electrode tip. So, the distance between the last point or the end of the contact tube and the electrode tip through which the current flows during the welding is called electrode extension. So, stick out of the electrode is the portion of the electrode which is projecting from the contact tube and is termed as the electrode extension, and the electrode extension affects the weld bead penetration and the deposition rate, because it directly affects the electrical resistance heating. Greater is the electrical resistance heating, greater will be the deposition rate, but it decreases the penetration, decreases the extent of the penetration. For the short circuit metal transfers, normally 6 to 12 ampere electrode extension is normally used, but for the globular and the spray transfers 12 to 25 electrode extension is commonly used. So, if we see the increase in electrode stick out increases the melting rate because of the increased electrical resistance heating of the electrode extension part, and it also it decreases the penetration due to the increased resistive heating of the electrode itself. Too much electrode extension increases, although increases the melting rate, but it makes difficult the placement of the weld metal in the required position, and the weld bead morphology is or weld bead shape is also adversely affected. So, that is why the electrode stick out and the electrode diameter, these two things significantly affect the selection of the welding current. Inappropriate electrode stick out and the electrode for a given diameter, inappropriate selection of the welding current for a given electrode stick out and the electrode diameter can adversely affect the penetration and the weld bead geometry which is developed. Now, I will say so this is what we have said, that if really we want to develop too high heat while welding the thick sections, high penetration is mandatory, then it will be necessary to use the high welding current. So, for working with the high welding current, it is necessary to go with the large diameter electrodes so that the required amount of the heat can be generated. And with these we use the small electrode extension in order to obtain the optimal weld bead geometry. In general, increase in welding speed reduces the penetration and increases the weld bead size. It has been observed that the for a given welding current and for a given welding voltage, when the welding speed is increased for a particular speed, the welding the penetration of the weld bead is found to be maximum, and the lower and on the higher side the weld bead decreases the penetration, and this happens when too high welding speed is used, it decreases the net amount of the heat being supplied to the base metal for the melting, and when too low welding speed is used, most of the heat is supplied over the top of the weld pool, and metal is not, and heat is not able to penetrate down into the base metal. So, the lower and the higher welding speeds both do not help much in achieving the desired depth of penetration, but an optimum speed results in a maximum penetration. If we see this diagram, it will clearly indicate this is the contact tube through which electrode is coming out. So, the end of the contact tube and this end of the contact tube which is supplying the current to the electrode and the tip of the electrode. So, this portion which is this portion of the electrode which is projecting out from the contact tube is called electrode extension, and the gap between the electrode tip and the workpiece is called arc length. So, if we see if we increase the electrode extension, and then for a given welding current of 1 electrode size, then it is desired that the electrode extension with the increase of the welding current, electrode extension should be decreased. Like we can work with the larger electrode extension when we are using the small lower current. When high current is used with the 1 electrode size, the smaller electrode extension should be used. While we can use the we can use very with the high current, it is required to work with the large diameter electrode. So, the electrode extension for this shows that electrode extension can vary from the 6 to say 18 or 20 mm, but the range of the current will vary according to the diameter of the electrode which is being used. For example, this can work with the 200 to the 300 ampere range, while it can work with say about 50 to the 100 ampere welding current range. So, the selection of the electrode extension and the welding current is important for a given electrode diameter. Inappropriate selection can lead to the poor weld bead shape and poor penetration. However, we can get the higher the deposition rate. Now, we will see the another important aspect related to the gas metal arc welding process is that the metal transfer. This metal transfer is observed in all consumable arc welding process where electrode tip melts and the molten metal is transferred to the weld pool. In case of the gas metal arc welding process, the transfer of the molten metal takes place drop by drop from the filler metal to the weld pool, and generally it occurs this transfer of the molten metal drops. It takes place in the two ways. One is by touching to the weld pool, that is the short circuiting mode of metal transfer, or in form of the transfer of the discrete drops moving from the electrode tip to the weld pool. So, this discrete transfer of the molten metal in form of the discrete drops can be in form of globular or the spray type. So, the drop transfer can be the globular or the spray type, which can happen under the different conditions. You know that depending upon the welding conditions being used, the various the size of the drop, shape of the drop, and the direction in which it is moving, and the type of the metal transfer which will be occurring can be affected by the various factors related with the welding. For example, the type of the current and the magnitude. In general, the DC current affects the metal transfer in very systematic way as compared to the AC. Increase in the welding current magnitude shifts the mode of metal transfer from the globular to the spray, especially when the gas shielding gas is argon. So, this happens mainly because of the reduction in surface tension force and the increase in pinch force magnitude, and the variation in the melting rate. Current density is another important factor that affects the size of the droplet and the mode of metal transfer. Too high current density will be causing the faster melting, and the higher pinch force will be decreasing the size of the drop being transferred. The electrode composition will be affecting to the electrical resistivity, and it will be affecting to the way by which molten metal the melting of the electrode tip is taking place at the electrode tip is taking place, and then it is transferred to the weld pool. Electrode extension will be affecting to the electrical resistivity, and accordingly the rate at which molten metal drops will be developing at the tip of the electrode. Shielding gas on the other hand affects the the whether there will be a rotary type of transfer or the spray or the globular transfer or short circuit mode of the metal transfer, because it affects the heat generation, because heat generation due to the difference in the ionization potential of the various gases, and the metal transfer also is affected by the characteristic of the power source being used, whether it is the constant current type or the constant voltage type. So, if we see the common types of the metal transfers are the short circuiting transfer or globular spray or the drift transfer, depending upon the welding current and the electrode diameter being used, shielding and the shielding gases which is being used, we can have these common type of the metal transfers in the gas metal arc welding. Say this is the schematic diagram showing the arc between the electrode tip and the workpiece, and here electrode tip is touching to the weld pool and then molten metal drop being formed at the tip is getting transferred. So, this will be leading to have the short circuit metal transfer, and here slow melting of the electrode tip will be leading to the development of the molten metal drop to the larger size, and then it is getting transferred under the gravitational force. And when the current is too high, then the rapid melting and the high pinch force will be causing the detachment of the droplets when they are of the very fine size, thus leading to the spray kind of the transfer. So, increase in the welding current changes the mode of metal transfer from short circuiting to the globular and then globular to the spray. Increase in welding current over a narrow range leads to the significant increase in the drop transfer rate per unit time, coupled with the reduction in the volume or the size of the drops being transferred, and this happens mainly because of the two regions. Means increase in the welding current increases the drop transfer rate and decreases the size of the drops being transferred, and this happens because of the increased melting rate of the electrode and increased magnitude of the pinch force. If we see here in case of the gas metal arc welding process, the schematic diagram showing this diagram showing the relationship between the arc voltage and the welding current. If we see here, when the welding current is increased for a certain range, the mode of metal transfer remains the globular kind and the drop trans, and when we increase the welding current beyond a certain range, we find the spray kind of transfer, and in between the mixed mode is observed. Further, if you see the current magnitude is increased, then the number of transfers, then the number of the drops being transferred per unit volume, per unit time, or the volume of the drops, the relationship between the welding current and these two characteristics, that is volume of the drop and the number of drops being transferred. So, if we see here a schematic diagram showing that if we increase the welding current, then the volume of the drops decreases rapidly and the number of drops increases significantly, and there is a range of the current over which this variation in the volume of the drops and the number of drops takes place very abruptly. So, this the value of the current or a narrow band of the current is called a transition current, across which the change in mode of metal transfer from the globular to the spray takes place. So, this is where you can say the number of drops being transferred in the globular are very less, maybe 10 to 20 drops per second, while these can be in range of 250 to 300 in case of the spray mode of transfer. So, the transition current is to be crossed to have the spray mode of the metal transfer. The pulse MIG is one variant of the gas metal arc welding process, which is commonly used, especially when the low heat input is required for developing the sound weld joint. In this case, current is varied between the background current and the peak current levels. In pulse current base, it is based on the principle of pulsation of the welding current between high and low levels at the regular interval of the time, like in the pulse TIG welding process. So, here current is varied between the background current and the peak current levels, which in turn peak current helps to melt the electrode tip and the transfer of the droplet, and during the background current portion the solidification is facilitated. So, if you see the high current is termed as peak current, primarily used to melt the Feng surfaces of the base material and the electrode tip, while the low current is generally called background current, performs the two function. One, it helps to maintain the welding current while generating the low heat input, and further it allows the time for weld metal to solidify by dissipating the heat to the base material. So, now we conclude this presentation. In this presentation we have seen the basic principle of the gas metal arc welding process and the important parameters which play significant role in development of the sound weld joint. We have also seen that what are the power sources which can be used with the gas metal arc welding process, and the effect of the polarity on the quality of the weld and the weld bead which is made by the gas metal arc welding process. Further, we have also seen that how the one variant of the gas metal arc welding process, that is the pulse gas metal arc welding process, and this one is mainly used when the low heat input is important for developing the sound weld joint, like the metals which are very sensitive to the heat or low heat input is required for developing the weld joint, like in the odd positions like vertical or the overhead welding conditions. So, now thanks for your attention, and in subsequent lectures we will be presenting the some other welding processes. Thanks for attention.